This is a series of videos to demonstrate the noise parameter measurement system using the Agilent PNA-X and option 29 native noise receiver. With this particular apparatus, we'll be using a 50 gigahertz Agilent PNA-X, the N5245A. This is a 4-port version with the integrated noise receiver on port 2. Using a wafer prober, manual Cascade 11K wafer prober, and a Focus Microwaves CCMT 2 to 50 gigahertz source pole tuner. Now this particular tuner has a crossover frequency of 10.3 gigahertz, so the measurement bands need to be split up accordingly. We will calibrate and measure in blocks from 2 to 10 gigahertz and then 10 to 26 gigahertz. For this demonstration, we will omit a third band, which normally runs from 27 to 40 or 50 gigahertz when the devices allow you to measure that high. In order to perform this measurement, we utilize Gore FaceFlex cables. These are the purple ones that are a little pricey, but well worth every penny. And then the calibration will be performed with Agilent equipment. We have a 15 dB ENR 50 gigahertz. This is the 346 CK01 noise head. And then a pair of 50 gigahertz electronic calibration units from Agilent. This one right here is a 50 gigahertz with 2.4 millimeter female connectors on both sides. And this one over here has the male connector, which is used during the calibration. If you don't have that extra standard, you can either use mechanical standards or do an adapter characterization onto one of the ports on the other eCal. So I'm going to get started with the procedure by showing the PNA-X screen and some of the steps that we go through in order to perform the calibration. So here we go. Let's go ahead and get started with the noise calibration. We're going to go into the network analyzer menuing system. Zoom in a little bit here. I'm going to go to Response, CalWizard. And since this measurement class is a noise system, it already knows that we need to do a full noise calibration instead of just a scattering parameter calibration. The calibration method we use for this technique is scalar noise. Scalar noise sets up the network analyzer such that the internal electronic calibration system is not utilized. The source pulling system is not used internal to the network analyzer. This allows us to override it externally. Think of it that way. The receiver characterization will be performed with a noise source. We keep this radio button over here selected to noise source. It's important to have the ENR table, the excess noise table for the noise head, presented to the system. Go ahead and click Next. Now we have to go ahead and pick the cal kits. We're going to use the electronic calibration system. For both port 1 and port 2, the DUTs, or the probes, in this case, are 2.4 millimeter female connectors. So those are selected, and the eCal is selected for this. And for the noise source itself has a 2.4 millimeter male connector on it. And with that, we're going to actually perform a full vector calibration at that same reference plane. So we have this de-embed noise source adapter highlighted. We'll go ahead and have this set up. Now the user 1 is a characterization within the eCal that we performed here that allows us to put a particular male-male adapter on that side of the eCal and actually perform a calibration as if we had that standard. So go ahead and click Next, and the first step here is to attach a noise source to port 2. We'll go ahead and perform that since that's already connected. Now what you see on the menu, on the windowing down below, is the system will be measuring the excess noise with the noise receiver We'll actually perform this 3 times. Internal to the network analyzer is an LNA. The LNA can add 0, 15, or 30 dB of gain between your excess noise and the actual receiver. And because the system doesn't know what level you're going to have it set at, and they want to allow you to be able to change that during your measurements, they go ahead and just calibrate all 3 of these at once. We always have it set to 30 dB of gain internally, and have never had any problems at all with overloading the front end. You'll definitely know if you do. So now that step is complete, you'll see the wizard is now asking for the ecal, and it says in the middle here, it says it's looking for user 1. So this is the ecal with the male-male adapter on it. We'll go ahead and pause for a minute. We'll hook that up to port 2 and proceed. Okay, we're now at the step where the noise head has been presented to the network analyzer. Now it's time to hang a set of mechanical standards, or in this case the ecal, onto port 2 and go ahead and get those measured at the same spot that the noise head was presented at. So we'll go ahead and click measure here. We'll see a series of measurements occurring on the screen. Interesting thing to note here is that it appears that the network analyzer is not only taking measurements of these standards into the noise head, but it's also going back and using the VNA receiver that's on port 2. Since these are both available simultaneously without any mechanical switching, the system can actually measure both of them without any issue. The next step after this will be to connect port 1 to port 2, and that will allow their internal code to complete the calibration. What this means in the end is we have absolutely complete full vector correction all the way down to the noise receiver. And that's made possible by the fact that there's a network analyzer in there, and there's a second a full VNA in parallel with it. So go ahead and let this complete. Once again, some of these steps are performed at multiple gain settings for the noise receiver, just so it will be ready for all three states should you choose to change it during measurement. We'll go ahead and pause and connect port 1 to port 2 with the 3-foot long 2.4 millimeter cable. Okay, here we go. We've connected port 1 to port 2, and we'll go ahead and click measure. Again, there are a number of steps that are performed for all 3 of the gain stages with the network analyzer. This step takes approximately 1 minute, and in the case of the measurements that are performed in this setup today, the frequency steps are from 2 to 50 gigahertz in 100 megahertz steps, and so that's a little bit higher resolution than what's required for noise parameter measurements, but it's performed here today so we can demonstrate part of what we're seeing in the raw noise figure measurements under source pole. Okay, so port 1 and port 2 have been connected up, and that's completed, and now it's time to perform a conventional calibration down at the end of the cables. So it's asking us to present standards to the end of the cable. So this is the first time that port 2 will actually have its cable extended, the one that will eventually hook up onto the probes. So we'll pause and connect the ecal to both ports 1 and port 2. So here we go with the final measurement step. Okay, the calibration is completing. And the method that's used in this system is that the calibrations are always stored within the state files themselves, so I don't really need to worry too much, at least on this step. I don't need to worry about saving the cal state. I'll go ahead and just click Finish. And then right away I'm going to go over and click Save to know that my calibration is stored in part of the noise cal state. Now the results that you see in the upper left screen are a little confusing, but then again we're looking at the noise figure into the ecal presently, so there's really not much to worry about at this point. The next step in the calibration actually involves preparing for the adapter characterizations. We're going to go ahead and leave the noise cal state. We're going to go over to a state that's referred to as a cable calibration from 2 to 50 gigahertz. We'll go ahead and load that up. The important thing to note is that the electronic calibration that was used as the last step of the noise measurement is still connected to the system right now. So we're not disconnecting and reconnecting cables any more often than we absolutely need to. So we'll go ahead and go in here and invoke the Cal Wizard, do a Smart Cal, go ahead and select a 2-port calibration, 1 and 2, 2.4 millimeter females. Going to go ahead and make sure that it's pointed at the proper ecal. Go ahead and click Next and get going on the measurement. This very much is just the straightforward at the end of the cables electronic calibration, nothing more. As we'll show in the diagrams later, there's reference planes that are created at the end of the cables, reference planes that are created either at the end of the probe tips or on wafer, and then what we'll have to do is create a de-embedding file in order to get us from one to the other. So in order to do that, we actually need to know where this reference plane is. When we finish this step, we'll go ahead and save this one by name, as we'll need to be able to look it up a little bit later. These videos were recorded on November 2nd of 2013, so you'll see the number 1102 in some of the naming conventions, just a handy way of remembering when these were made. This is a lot more exciting in person. Okay, so this electronic calibration from 2 to 50 is just completing up. When we save this, we'll go ahead and give it a name and put it in the table. So before we hastily click Finish, we'll go ahead and click the Save As button and enter a name. So we'll go ahead and say Save As User Cal Set, and we will call this Cable Cal 1102. Go ahead and save that. And then it's important for me to save it in the state file as well. So I have that saved. Once again, before moving the cables or anything, I'm going to move on to the next state file. This one is called Tuner Cal. There will be a couple of steps we have to do in order to characterize the tuner in its positions. And I have a state file set up for this. This one is pretty straightforward with a couple of caveats. We're still spanning from 2 to 50 gigahertz. And I bet this is not set up right. We're going to go ahead and check our points. This is not set up properly, so we're going to go ahead and pause for just a moment here. Okay, we're in the Tuner Cal state file. what we have set up here is we're sweeping from 2 to 50 gigahertz in 100 megahertz steps. Very similar setup to the other the cable calibration that you saw. The only spin here is that we actually have two different channels running on the PNA-X here, and the top two windows and the lower left window, these are all running from channel 1, which happens to be a full two-port calibrated channel. What we're going to do over in the lower right is we're going to set up a calibration that's actually a one-port calibration on port 2. I know that's a little confusing, but once again the block diagrams should reveal a little bit more as to why we're doing this. So in order to get a calibration on this, we actually have to cal twice. So we're going to go to channel 1 and run the calibration very quickly. It's a two-port cal on ports 1 and 2. Using the eCal, we'll go ahead and click Next. We'll get this cal running. This takes about the same amount of time as the last one. I'm going to go ahead and pause this one here and we'll come back right before it ends. Okay, the first channel is nearly done calibrating, so we'll go ahead and finish this up. And although this doesn't get referenced anywhere other than for verifying we got everything right, I do go ahead and save the name of this. We'll go ahead and save it and call it Tuner Cal CH1 and give it the date, because that's calibration pertaining to the first channel. In order to get the second channel calibrated, we need to select it. I find it easy to just click in the window. We'll go into the Cal Wizard again, Smart Cal. Here we need to select a one-port calibration on port 2. And then we have to tell it that it is, the DUT is going to be a 2.4 millimeter female. Pick the correct eCal. Go ahead and get that calibration going. This will take less time because there's only one port to calibrate instead of 2. This calibration step is completed. We'll go ahead and save it again, and we'll call it Tuner Cal Channel 2 for the date of November 2nd as well. So now we have both Channel 1 and Channel 2 are calibrated with a 2-port and a 1-port calibration in this tuner state file. We'll go ahead and save Tuner Cal, and we'll be done with that. After all of the mechanical calibrations have been completed, it's time to hook the cables up to the probes. Now in the case of port 2, we're using a shorter 1.5 foot long Gore cable that goes from port 2 directly down to the port 2 set of probes. I have a set of Pico probes on here right now, 50 gigahertz GSG 100Ps. And I also have very good luck with Infinity probes, I-50 GSG 100s and I-50 GSG 150s. Now on the port 1 side, the longer Gore cable extends into the source tuner. So we have a reference plane we can think of right on this side of the tuner. And then on the other side of the tuner, we're going through an Ritsu 2.4 millimeter barrel to a flexible piece of 2.4 millimeter coax. So we have about 5 or 6 inches of coax from the side of the tuner down to the input side probe. All of this will become a part of the characterization for the tuner. So we'll be taking a number of measurements from the left side of the tuner down onto the reference plane just past the probe tips. So we'll go ahead and get a calibration down at the probe tips and make a couple of de-embedding files to get ready for the tuner cal. Okay, so we have the cables hooked up to the probes. The tuner is in the initialized position, but it is in line presently. And we're going to do an on-wafer calibration. Now, this can be performed by any means you would like. There's certainly opportunity within the Agilent PNA's own CalKit system to perform this. If you have TRL standards and a TRL CalKit that would allow you to do this there, that's perfectly fine. I'm using WinCal. We're comfortable with it. The particular calibration technique that you use for this really needs to be matching the standards that you have created, matching the techniques that you've created. If you have TRL, use TRL. If you don't, use something you're more comfortable with. That's not really a part of the noise system per se. It's much more application specific. So we're going to go ahead and just step through the standards here. I'm already touching the open standards that are on the wafers, so we'll go ahead and get those measured. I'm not going to move the screen over. I'm watching the network analyzer on the other screen. I have a state file running there that runs from 500 megahertz to 50 gigahertz in 100 megahertz steps. This not only will allow us to get the calibration that we need to create de-embed files, but it will also allow us to take scattering parameters of the device once it's under test. Okay, I've moved over to the shorts. So we're going to go ahead and measure port 1 short, port 2 short here in a moment. If you're not familiar with WinCal, this is Cascade Microtech WinCal XE. And more information can be found at cmicro.com. And it's a pretty fantastic product. It has all of the famous acronyms for calibration standards, standard techniques built in. You can use the ISSs that Cascade will sell you to go with the probes, or you can go ahead and deselect that and put in your own coefficients, your own techniques. TRL, LRRM is a favorite of ours as well. Okay, the last step in the calibration is to step on the through path, and in this particular case we measure switching terms internal to the network analyzer as well as the actual S12 through path. Once this is completed with WinCal, we'll ask it to compute the error set, and then we'll send it down to the network analyzer and we'll give it a name that we remember, in this case LRRM50G1102. And now that's been stored in the network analyzer. We'll move back to the network analyzer for a few of the next steps. Inside the network analyzer, we need to go and look at the calibration cal sets that are being managed. We'll note here that the LRRM50G1102 description is here at the top, and it's actually selected. We're going to go ahead and just very quickly copy the name over, the description over to the name. So that's listed there. Go ahead and close that. We'll save the state file because we'll use that during the measurements as well. Now here's the trick. We need to go over to the utility macro adapter characterization. And what we'll do here is we will pick for the first cal set, this is a probe head adapter type. For the first set we'll pick cable cal November 2, and then for the cal set down at the reference plane we'll select the LRRM50G1102, which we just completed. Go ahead and characterize that, and we'll store it as P1 de-embed with today's date on it. Similarly, we'll go to port 2, characterize and save. We want to have very consistent names here just so we can find them. This is port 2 de-embed, November 2. So now we've created a de-embed file that will get us from the port 1 cable end to the input of our device under test. And we also have one that will get us from our port 2 end of cable down to our port 2 device under test. We're going to go ahead and load the cable calibration for a moment here. Remember, the reference plane in this is back at the cable ends, so we should see in the lower left corner with S21 we do see a little bit of loss here because we're going through the tuner in its initialized state. There's a little bit of coax loss after the tuner, probe loss, and so on. I'm going to go ahead and go in and say response cal fixtures fixturing on, response cal fixtures 2-port de-embedding. In this window we'll enable the de-embedding. For port 1 we will go ahead and pick the port 1 de-embed that we just created. And then for port 2 we'll pick the port 2 de-embed that we just created. For a moment here, what we'll do is we'll look at, go ahead and zoom the scale way in on S21. You see that we have just a couple hundredths of a dB of error. And it should be closer than that. That's a couple hundredths of a dB, way out at 50 gigahertz. That's fine. That's good enough for me. The point here is to make sure that we've actually added everything up correctly. So we'll go ahead and cancel that. Now I want to go in, we'll go right back into the fixturing 2-port de-embedding, and now I want to take port 2, and just for a moment I want to say there's no port 2 de-embed. So what we're measuring here is the electrical loss from the port 1 reference plane back to port 2's cables. So we'll go ahead and just save this file as port 1, what should we call this? We'll call it 0 picosecond through from 2 to 50, 1102. Our on-wafer standards actually have no electrical length to them. We shorten the length in order to eliminate that. So nevertheless, we're going to save this scattering parameter file as the 0 picosecond through path. And remember that the measurement is going from left to right, and so if we were to use this as a de-embed, we now would actually have to tell it to reverse the adapter ports. We'll go ahead and save this. We've got today's date on it so we don't lose track of it. And now what I'd like to do is go over to the tuner calibration, if you remember this, and we have 2 channels that we need to set this up on. So I'll select channel 1, I'll say response cal fixturing on, response cal fixtures 2-port de-embedding, enable de-embedding port 2 only, use the file 0 picosecond through from 2 to 50, November 2nd, and reverse the adapter ports. That takes the measurement that we performed and drops it in on port 2. So the only thing that's remaining is from the port 1 cable down to the DUT. And this will allow us to actually take a direct 2-port measurement of the tuner and the cabling surrounding it for de-embedding. And we have to do exactly the same thing on port 2. So we'll say fixturing on, response cal fixtures 2-port de-embedding, enable port 2, user defined reverse adapter ports 0 picosecond through. Okay, we're going to go ahead and do a tuner calibration here. We're going to go and load the tuner cal state file, and we've set up all of the de-embedding from the previous step. So now it's a matter of just starting up the state file. First step that the program will do is it will copy this state file up to 3 times. Right now we've done all of the calibration and de-embedding from 2 to 50 gigahertz. We'll go ahead and split that up to span the different measurement ranges, the 2 to 10, the 10 to 26, and the 26 to 50. In this particular case, we're going to go from 2 to 10.3 gigahertz in 100 megahertz steps, and then 10.4 to 26. And we're skipping the higher frequencies just because the devices we need to measure don't extend beyond that range. We're going to go ahead and start the system up. This will look confusing for a little while, but we're going to be moving the tuner to its first initialized state. And then you'll see a spirograph pattern on the right side. In the upper right, this is S22 from the de-embedding of the tuner. In the lower right is the gamma source that the device will actually see. And the software will store both an S2P file and an S1P file for every position that the tuner is moved into. We've experimented with the tuner pattern quite a bit, and right now we're settling on approximately 60 states. I know that other extraction techniques can use far fewer than that, but that's what I'm using presently, and it seems to work just fine. The other aspects of the system are fast enough that we're not terribly concerned about the number of states that are measured. So this is what the device is seeing with the tuner in the initialized position. We're going to go ahead and move the tuner into a position where there's a very high reflection coefficient presented, and then we'll take a quick measurement. So here you see that there is indeed a higher reflection coefficient that's presented to the device. So you can see it up here, and then this is the actual gamma source that you'll see from 2 to 10.3 gigahertz in 100 megahertz steps. So most of them, they're all floating around in the 0.77 range for this particular case. The other thing to note here is the relative phase. We've got 29.86 degrees on the one port, the gamma source. You see that it's 30.49 degrees from the 2-port measurements. These are very, very similar to one another, and that should be comforting to us to say, okay, we've probably got all of the calibrations right. These are nearly matched up. There's a subtle difference between the two. So now it's just a matter of letting the software keep running through, and we'll characterize the tuner in all of the positions from 2 to 10 gigahertz, and then we'll move to the next state file and do the same thing from 11 to 26 gigahertz. This step typically takes between a half an hour and a whole hour, depending upon the measurement resolution and the number of states. The last step that needs to be performed before we can take noise measurements is that of setting up the de-embedding within the noise measurement system. We're going to go ahead and load the noise cal state file again. Remember, this has the cable calibration for noise figure in it, but we have not de-embedded down to the reference plane on the wafer yet. You can see the noise figure number is slowly creeping up as if there's additional loss that needs to be de-embedded. So we'll go ahead and go in and say response cal fixtures, fixturing on, response cal fixtures, 2-port de-embedding. We will enable de-embedding, and on port 1 we will pick the port 1 de-embed file. On port 2 we'll do the same, the port 2 de-embed file. And at this point, when we look at noise figure, we'll see that we're hovering about 0 dB all the way through, in this case, to 50 gigahertz. If we were to look at the absolute noise power density normalized to 1 hertz, it's right down here at the bottom of the screen. You see that we're actually flirting with minus 174 dBm per hertz. all the way to 50 gigahertz. Sure, the uncertainty is going up a little bit at the end. That gives us a little bit of a warm fuzzy feeling. We'll go ahead and save this calibration. I wanted to note something here. Let's go back and look at the fixturing, 2-port de-embedding. Now with port 1, we've selected the port 1 de-embed file that we created. This file is only valid for when the tuner is in its initialized position. When we move the tuner to another position, we will need to place a different de-embed file in to account for the additional loss. We can think of it that way. That's what will happen during the measurement steps. Every time the tuner moves, the controller code will go to the library of de-embed files that were captured during the tuner calibration process. We'll just keep dropping these in. So although the device will be presented a different reflection coefficient every time, the measurements will remain corrected through the de-embed process. So in essence, there's no additional math that needs to be performed on the actual noise figure measurements that come out of the instrument. We can go directly to an extraction once they're captured. So this state file has been saved. And once again, through a little bit of software trickery, this state file will be saved to 2 or 3 different state files. We'll break it up from 2 to 10 and 10 to 26 gigahertz, such that the measurements can occur on either side of the tuner gap. So now we actually have both the 2 to 10 and the 10 to 26 gigahertz system ready to go. We're now to the point where we can take noise parameter measurements. Presently on a state file that will allow me to see the device under test being measured for scattering parameters, and I actually have the device biased to up with 3 volts drain voltage and 20 or 30 milliamps of drain current, just to see that the device is awake and alive. This particular device doesn't have a lot of gain past about 26 gigahertz. You can see that there's a little bit of calibration issues right up at the end of 50 gigahertz. That's totally acceptable. That's outside of the range that we were really concerned about. I'm going to go ahead and start the controller program. And what the controller program will do, you can see it's already turned the power supply off. It will go ahead and load up the scattering parameter state file, shut the power off, and then find the bias conditions for the device. The idea is that we're going to seek a gate voltage to find a particular drain current, and then we'll record those in a table. So when we're taking noise measurements, we'll be able to sit there and work our way through that list as rapidly as possible. We're just going to keep going back to these same values regardless of the fact that the source tuner is in a different position. Once the bias points are found, we'll step through, and in this particular state file you'll see S2P files being captured. These S2Ps will eventually be a part of the extracted noise parameter results. These aren't used as a part of the noise figure measurement. They're merely sent out as part of the noise parameters in the touchtone format. So I believe there are 4 bias conditions being run in this particular DUT. So once the 4th sweep completes, the noise state file will be loaded up. It's the one with the 5 different boxes, 5 different graphs in it. And the tuner will be reinitialized as it's presently in. And then we will move to the first position. Pretty shortly here. Okay, so at this point, separate point on it. At this point, what we're measuring is the noise figure from 2 to 10 gigahertz with the tuner still in the initialized position. I have a small message up here that tells me that the tuner is still initialized. You can see that we have a very well-behaved, monotonic, more or less monotonically increasing noise figure ranging from approximately just under 1 dB up to approximately 2 dB, and that's to be expected for this particular device. You see a little bit of ripple as we go through here. Remember that the device is being presented what it's being presented. There's no source correction going on with the eCal. This is just a scalar noise figure measurement as it's called out in the cal. And then the code is actually stepping through very slowly and running this on all of the bias conditions. I should have let that run here. So go ahead and step through that. Once it's completed the fourth bias condition, this is where the fun begins. We'll go ahead and move the tuner to a new position. It'll look a little weird here for a moment. The tuner will move and the de-embed file that goes with it will be presented. And now we'll take another measurement in this new position. In this position we have somewhat of a reflection coefficient, probably about 0.2. We would have to look it up. But what you see here is a ripple in the noise figure. This is because at one particular frequency we happen to be close to F-min, but then as we rotate our way around the Smith chart, we get farther and farther away from F-min. Rotate around, we're closer, farther, farther. And if we look at the steps here and the spirographs from the tuner step, we'll actually be able to see a correlation here. I'm going to go ahead and run this on all four bias conditions so you see a little bit of motion. There's a little bit of averaging going on, and then a step in bias. Now you raise the bias and the noise figure can kind of take off at higher frequencies. Once all of these states have completed, the same thing happens. The tuner will move to a new state. The corresponding de-embed file will be dropped in. There we go. Now we have a very high gamma, so we're actually rotating around more or less the outside of the Smith chart, and you can see that we are still occasionally getting close to a minima, these lowest points on the chart. But when we wrap around, we're very, very far away from F-min, and we see more noise figure. So what this tells us is that we're slowly working our way around different positions on the Smith chart to capture noise figure. Now this code is moving the tuner and then sweeping through the bias conditions and applying a little bit of averaging. So you can see that we spend just a few seconds at each bias point in each state. The order of the measurements is performed to minimize the amount of wear on the mechanical tuner, and the motion of the mechanical tuner also is the slowest element of this measurement. So we would want to do everything we can by moving the tuner as little as possible. The tuner is actually moving the carriage from right to left in one pass for this 2 to 13 gigahertz sweep, and then varying the gamma, the z-axis motor, if you will, as is required as it works its way across. This also is optimized for optimized for speed. So in this particular case, to run from 2 to 10 gigahertz would probably be 10 to 15 minutes worth of measurement time for this particular sweep. It's also a little bit faster if instead of measuring in 100 megahertz steps in order to reveal this pattern, instead we would just measure in 1 megahertz steps. Now you can't see this aliasing, this ripple in the measurements when you do that, so it's harder to convey what the system's actually doing. but it does speed up the measurements quite a bit, and when we're extracting noise parameters on only 1 or maybe even 2 gigahertz steps, it's really unnecessary to perform 100 megahertz measurements all the time. Okay, so the system has completed all of the measurements from 2 to 10 gigahertz, and now it's time to move on to the next frequency band. So the tuner will be initialized. It's actually occurring right now. And when the tuner initialization completes, the new state file will be loaded. I'll go ahead and go back to this screen. Now we're loading up the 10.4 to 26 gigahertz measurement. The proper de-embed file will be applied. And again, the first thing we do is we measure with the tuner in the initialized position. As you see, as you go up and up in frequency, the reflection coefficient presented to the DUT in this initialized position is not as clean as before. It's not as much the effect of the tuner as it is the effect of the entire apparatus. This is measured at 4 points, and then the tuner will move to a new position. The corresponding de-embed file will be dropped in again, and then we'll see the noise figure. I'll go ahead and maximize this again. And very shortly the new state file will drop in when the tuner moves. So we have a very small reflection coefficient, but nevertheless we're starting to see the ripple show up in the noise figure measurements. We can also look here to see where the absolute noise is, and you can see that the orange line, the DUT NPDI, once again this is in dBm per hertz. At 10.4 gigahertz we're measuring something on the order of minus 162 dBm per hertz. That gives us a certain amount of confidence that this is a half decent number. So we're not flirting with the measurement floor that we saw earlier. It was on the order of minus 175. Of course, you can see the ripple in this as well, and the assertion we have is that the ripple is very real because of the environment that the device has been placed in. I can see from another screen we've just increased the reflection coefficient to be something very, very high, and you can actually see a significantly higher ripple in the normalized noise, excess noise from the system. And the noise figure is revealing that as well. In order to measure all of the points, the noise figure points across the gamma space, in this particular configuration it would take approximately 1 hour to complete. That's with 4 or 5 bias points. In order to speed up the system, we reduce the number of measurement points to just go in 1 gigahertz steps. Usually when that's the case, we can measure from 2 to 50 gigahertz in 1 gigahertz steps for 10 bias conditions in 1 hour.